Once we have derived the discriminant functions, we can assign new cases to their predicted classes. Assigning new cases is easy. We simply assign new cases to a class based on the distance between the case and the class centers, also called centroids, as we discussed in cluster analysis before. In a single variable situation, the cluster centroid is simply the average of the values of the predicted variable of all the cases that belong to that class. In a multiple variable situation, though, a class centroid is a vector of the means of each of the predictors from all the cases that belong to the class. The shorter the distance, the more likely the new case would belong to that class. For example, in the simple example with only one variable, income, if the class center or the average income of all the customers who accepted the offer is $100,000, whereas the class center or the average income of all the customers who rejected the offer is $55,000. For a new customer whose income is $88,000, we would classify the new customer to the accept group because his or her income is closer to the class center of the accept group. What if we have more than one predictor variable? How do we measure the distance between the new case and the class centers? As we discussed the distance measures before, the most commonly used distance measure is the Euclidean distance. The Euclidean distance formula for computing the distance between a case with multiple variables, x1 through xp, and the class centroid with values x1 bar to xp bar is shown here. It is simply the square root of the sum of the squared differences between the individual values and the means. While it is a popular distance measure, Euclidean distance has its drawbacks as well. First, the distance depends on the units we choose to measure the predictor variables. So the predictors with larger values tend to dominate the distance measure. Second, Euclidean distance does not take into account the variability of the variables. For example, if the within-class variability of the income variable is very large, how can you tell if a customer who makes $88,000 is closer to the group with an average income of $55,000 or $100,000? Because the two groups would overlap substantially. Third, Euclidean distance ignores the correlation between the variables. Highly correlated variables tend to offer redundant information in the dataset, and therefore distort the distances or relationships between the cases. It is equivalent to only measuring the aerial distance without considering the terrain of the land if you plan to hike from one point to another point. You are going to be very misled by the aerial distance because it only provides you with the distance of a plane flying directly from one point to another, but does not take into account the need to go up and down the hills or cross areas of water. While we can use standardization or the normalization techniques to overcome some of these drawbacks, it is impossible to overcome all the drawbacks of Euclidean distance at the same time. So how do we solve this problem? For the reasons stated before, discriminant analysis uses a different distance measure called a statistical distance to address the drawbacks of the popular Euclidean distance. We are introducing the concept of statistical distance here because it is the distance measure used by discriminant analysis, So understanding it would give you a more accurate grasp of the concepts related to discriminant analysis. Also, statistical distance is a popular distance measure that can be used in many other analytics applications, such as cluster analysis, when the Euclidean distance is not appropriate or does not yield meaningful results. Therefore, understanding statistical distance adds another useful tool to your analytical toolbox. Statistical distance is also often referred to as the Mahalanobis distance, named after its creator, Indian statistician Prasanta Mahalanobis. It is unitless and scale invariant and takes into account the correlations of the variables. In other words, it addresses the three drawbacks of Euclidean distance that we discussed before. On this slide, we have the formula of statistical distance in the matrix notation. The formula shows that statistical distance is the square root of the product of the transposed matrix of the differences between the individual values and the means, the inverse of the covariance matrix S, and the matrix of the differences between the individual values and the means. This formula may seem intimidating. It actually is not. You can easily obtain the matrix of the differences between the individual values and the means by subtracting the value of each variable by the mean of the variable. For example, x1 minus x1 bar, x2 minus x2 bar, and so on, all the way to xp minus xp bar. And that would be the matrix of the differences between the individual values and the means. The notation apostrophe here represents transpose operation, which simply turns the column vector into a row vector like this. x1 minus x1 bar and x2 minus x2 bar, and all the way to xp minus xp bar. In the row form, the covariance matrix S can be easily obtained in Excel using the data analysis tool covariance matrix. The covariance matrix is also called variance covariance matrix because the matrix has the covariance values between the variables in the diagonal and the variance values on either side of the diagonal. The inverse of the covariance matrix can be computed using the M-inverse function in Excel. As you can see mathematically, it is relatively easy to compute the statistical distance. The other thing I want to mention is that the statistical distance is not that different from the Euclidean distance either. If you write the Euclidean distance formula in the matrix notation, this is what you would get. Euclidean distance is the square root of the product of the transposed matrix of the differences between the individual values and the means, and the matrix of the differences between the individual values and the means. So if you are familiar with the matrix notation, you can see that this formula is exactly the same as our previous formula of the Euclidean distance. Now if you compare this formula with the formula for statistical distance, the only difference between the two is the inclusion of the inverse of the covariance matrix here. By including the inverse of the covariance matrix, statistical distance has taken into account the correlation between the variables. In other words, when measuring distances, now statistical distance not only takes into account the aerial distance between 2 points, but the terrain between the 2 points as well. Now to illustrate the concept of statistical distance, let's look at a simple example of how statistical distance can be computed. Let's say we have two variables, x1 and x2. The average value of x1 is 25, therefore mu x1 equal to 25, whereas the average value of x2 is 105, so mu x2 equals to 105. For given case A, the value of x is 30, and the value of x2 is 100. So what is the statistical distance between the case A and the class centroid, which has the x1 value as the average value of x1, which is 25, and the x2 value as the average value of x2, which is 105. Suppose that the variance-covariance matrix of the two variables, x1 and x2, is computed to be this. As you can see, we have the covariance values on the diagonal, and then the variances on both sides of the diagonal. You can easily obtain this by using the data analysis covariance matrix tool in Excel. With this information, we are ready to compute the statistical distance. We'll first transpose the matrix of the differences between the individual values and the means. The result is a matrix in the row form with values 5 and -5. We then use the M inverse function in Excel to find the inverse of the covariance matrix. And by using the M inverse function on the covariance matrix here, we are going to get the inverse of the covariance matrix that looks like this. We then create the matrix of the differences between the individual values and the means, which is the matrix in the column form with the values 5 and -5. Finally, we find the square root of the product of the three elements here. And to perform matrix multiplication, you can use the MMULT function in Excel. The resulting distance is going to be 0.558. If you simply compute the Euclidean distance between the cases A and the class centroid, you will get 7.0 0.071. So as you can see, the statistical distance value and the Euclidean distance values are very different. If you want to better understand the computation of statistical distance, pause the video now and try to perform the calculation on your own to see if you get the same results. As mentioned earlier, discriminant analysis assigns the case to the class that is closest to it in terms of the statistical distance. However, software products would provide you with the classification functions instead of the statistical distances because they are easier to understand. The classification functions are equivalent to the statistical distances, but they are more useful in a number of ways. First, classification function looks like a linear regression model that produces a classification score if you plug in the predictor values. For example, these are the classification functions produced by R using the dataset of the 20 Sunnyvale Bank customers. As you can see, a classification function is derived for each class. So if there are 3 classes, then 3 classification functions are going to be generated by the software product. Each classification function has a constant value and coefficients for the predictor variables, as you would see in the regression model. For example, the classification function for class 0, which is the non-response class in our example, has the constant value of -6.25 and coefficients of 0.28 and 0.000019 for age and income respectively. So if we plug in the age and income values of the first customer, who is 44 years old and has an annual income of $99,000, we are going to get the classification score of 7.951 for class 0. And if we do the same with the classification function for class 1, which is the response class, we get the classification score of 7.324 for the first customer. Since the greater classification score is equivalent to shorter statistical distance in discriminant analysis, we predict that that customer belongs to class 0, which is the correct classification according to our data. You can pause this video and take a moment to compute the classification scores for the second customer in our dataset to see if that customer will be correctly classified or not. While obtaining the classification is useful, it would be more useful if the probability of the case belonging to various classes can be computed. With the probability values, we can rank the potential customers in terms of their propensity to respond and create performance charts such as the cumulative lift chart or decile-wise lift chart to assess predictive performance. Another important use of the classification functions would be to compute predicted probability of the case belonging to various classes. The mathematical formula for doing so is displayed here. the probability of a case belonging to a class is equivalent to the exponent of the case classification score for the class divided by the sum of the exponents of the case classification scores for all the classes. For example, as we computed earlier, the classification score for customer 1, who is 44 years old and has an annual income of $99,000, is 7.951 for class 0 and 7.324 for class 1. Therefore, the probability of this customer belonging to class 0 is the exponent of 7.951 divided by the sum of exponent of 7.951 and exponent of 7.324. The resulting probability is 0.652, meaning that there is a 65.2% chance that this customer will not respond to the home equity line of credit offer. Similarly, the probability of the customer belonging to the target class, class 1, is computed to be 0.348. So this again confirms the reason why we classified this customer into class 0. Please pause the video and try to compute the probabilities for the second customer in our dataset. Having the probability value would allow us to use a sliding cutoff value to determine whether we should classify the customer into the response or the non-response class. It also allows us to create the gains table to evaluate the performance of the classification model as we did before in classification cases. Finally, the classification functions also allow us to understand the relative importance of the variables in differentiating the classes. For example, is age or income more distinguishing or discriminant in predicting whether a customer is going to respond to a home equity line of credit offer or not? As you can see here, the classification functions look just like linear regression functions. And in linear regression functions, the coefficients often tell us the strength and the direction of the impact of one unit change in the independent variable on the value of the dependent variable. However, if we standardize the data before running the regression analysis, the coefficients will not only tell you the direction and strength of the impact of the independent variable in standardized terms, but also tell you the relative strength of the independent variables, because all the variables are on the same scale. So the same concept can be applied to classification functions here. If you look at the original classification functions derived from unstandardized data in our example, the coefficient for income is much smaller than the coefficient for age. And that is because of the scale of the income measure is different from the scale of the age measure. Since we are interested in finding the relative importance of the variables, not taking into account the scale of their measurement, we need to standardize the data before running the discriminant analysis. So here, I standardized our data into z-scores, which is unitless and scale independent, and then reperformed the linear discriminant analysis on the standardized data. and I got these classification functions that are presented here. As you can see here, now the differences between the coefficients for age and income are no longer very large. Because both measures are of the same scale now. The coefficients for age and income for class 0 are negative 0.16 and negative 0.26 respectively. In order to find out which variable is more important or a better discriminant of the two classes, we will look at the differences between their coefficients for each one of the classes. For example, the difference between the coefficients for age for class 0 and class 1 is negative 0.64, whereas that for the income coefficients is negative 1.06. As the difference with the larger absolute value means higher importance, we conclude that income has a more pronounced impact on determining the class the observation belongs to. This shows that income better separates the classes compared to age. If you can only choose one of the predictors in this case, you probably should go with income. From the analytics perspective, having the classification functions is more useful than having the statistical distance values or the discriminant functions. Therefore, the software output often provides you with the classification functions instead of the other measures. While in statistics, we tend to be more interested in statistical significance or goodness of fit. In analytics, we are more interested in predictive accuracy. Performance assessment for discriminant analysis is done in the same way as for other classification techniques, such as classification trees or logistic regression. We will discuss performance assessment when we demonstrate how to perform discriminant analysis using software packages.